I'm going to talk just a little bit about how we can have lots of electrons in one system. Because we spent all this time talking about quantum numbers and spent all this time talking about how you can't have an electron with the same quantum number. You can't have two of them in the same space. So how in the world do you have all these electrons together in one space and they don't have the same quantum number? So first of all, the person who kind of decided or figured out or postulated that you couldn't have more than one quantum number existing in a state was Wolfgang Pauli. And in 1925, he just said, okay, we've got quantum numbers. We got a quantum number for every electron, and no two can have the same number. And that kind of makes sense with atoms. Because when you look at atoms, it's like, okay, yeah, there's this number of atoms, there's this number of states, so that works really great. But what happens when we have molecules and lots and lots and lots and lots of atoms in one place, which provides lots of electrons? What happens? Because we talked about looking at what energy level exists for different electrons and perhaps like where they might be around the nucleus, but we didn't look at what happens when they have kind of the same state and they end up in the same place. So this is what happens. We're just looking right now at two traces of hydrogen atoms. We looked at that same thing last time when we talked about you're most likely to find the electron at the radius A0 and it may be somewhere else. And then you've got this other electron that has the same exact trace, basically. And they move together and they get closer and those actually kind of overlap and interact. And what happens is as those kind of probabilities move together, the energy levels actually split into little tiny sublevels. So they actually, with the n equals 1 level, you split it up, and there's still only n equals 1, but they're at just very slightly different energy levels. And that's what ends up happening. So the number of quantum states at any energy level basically is really small. So there has to be some way of splitting them up so that you can have enough energy levels for each electron. So basically, when you have one energy level, if you get to a certain point where the electrons start interacting, they just split into a whole bunch of different levels. And basically, each one of them can differ by just like 1 electron volt, which is not very much. That is a very, very, very tiny amount. But in doing though, you can have a very large number of electrons that differ just slightly, but still basically have the same quantum number, but not quite. And that's what ends up happening. So what we call this, we call these energy bands quasi-continuous. Basically, we just assume that when they split up, they just split up into a whole bunch of continuous levels, and each one gets a slightly different level. And then when we join atoms to form a crystal, we don't have the number of quantum states changing, but within each quantum state, each discrete level splits into a bunch of different tiny levels. So what happens is, let's say we have an atom, and we have more than one electron, and they can occupy up to like n equals 3. So there could be like n equals 1, and n equals 2, n equals 3. And we join all those atoms together, and what happens is all the energy levels split in some way. They all kind of split up, and basically to accommodate this factor. So the idea of quantum numbers is not violated when we get to single crystals and we have a lot of electrons. They still have different energies, they're just slightly different. So if the energy level is a particular value, it might be slightly higher or slightly lower, but most of all be the same. Now, in here, what we look at more than anything else is silicon or germanium or gallium arsenide. But those, basically, if we look at a silicon atom, 10 of the 14 electrons are bound and we don't concern ourselves with them at all. At the outer level, at the n equals 3 level, there are two different kind of splits. They split into S and P, which you learn about in chemistry. And the S level can hold 2, and then the P level can hold 6. So an isolated atom, silicon atom, out floating around in space, that's the way it's constructed. Basically, the 2 of the electrons in the outer shell are in the S, and then 2 are in the P. But what happens when you move these atoms together, basically the 3s and the 3p states overlapped and split. So what ends up happening is, if you're far away, you have the 3s state and the 3p state, where you have 2 n states and 2 electrons in basically the 3s state, and 2 electrons, but 6 could be there in the p state. But when they come together, the whole band splits and turns into this kind of dual level continuous energy distribution. So all of the lower electrons, and this basically when there's no energy in the system, all of the electrons initially go into this lower band, what's known as the valence band. That's where the 2 that were in the S level and the 2 that are in the P level both go there. Nothing is up in the conduction level. There's 4 possible places they can be, and there's nothing there. And this is at absolute 0, because there's no energy in the system. So everything goes to its lowest state. And there is a gap between the 2, which is called the band gap. That's E sub G. That's the band gap between the valence energy and the conduction. It's different for different semiconductors. For silicon, it's 1.12 electron volts. For others, it's different. But basically, every single semiconductor has 2 areas in which charge carriers live. In the valence band, which is the lower energy, and that's where everything is in the structure, or within the structure of the silicon. And then the conduction band energy level is higher, and that's where electrons are not bound but can kind of freely move around. At 0K, they can't do anything. They're just sitting there at the lowest energy level. So, oh yeah, I like it when my slides say what I just said. But yeah, it says what I just said. All the electrons are in what we call the valence state. When we add energy, we can actually move some into the conduction band, but we're not going to do that yet. How these bands form when they come together is related to how much, or basically what type of structure you have. So the electrical characteristics of the crystal itself and how they come together determines the current voltage relationships and determines the conduction of the electrical conduction, how these 2 bands are made. So it is sort of super theoretical at the moment. It will be, as we move on, we're not going to look at this funky picture. We're actually going to settle it out and make it look a little more reasonable. But the valence energy band includes all the electrons that are still bound in the lattice structure. They're still part of the structure. They can move, but only from one bond to another. They can't move anywhere else. They can kind of get enough energy to move just from one little bond to the other, but not much. The conduction band has all the electrons that have enough energy to leave the structure of the semiconductor. They're still there, they're still in the crystal, but they can go places, they can move. If you apply energy, they can go in a direction even. So if there are electrons available in the conduction band and you apply a voltage, those electrons will move, and they'll move in a direction. If you apply a voltage to for the valence band, things do move, but they move differently. Electrons just jump from bond to bond to bond. So when we look at this, what we end up doing is we end up kind of stretching this out and making it into a energy diagram in which the lower part is where the electrons that are part of the structure live, and the higher part is where the electrons that have energy live. And all materials are basically made this way, not just semiconductors, but all materials. So insulators have a really, really large band gap between the valence band and the conduction band, and they don't have electrons in the conduction band because there aren't any available to do that. They pretty much have a full valence shell, and they don't readily release electrons. So the energy gap between the valence and the conduction band is really, really, really big. So you have to apply a lot of voltage to get an electron to actually get into the conduction band and move. So that's why electrons are not conductive in insulators. Semiconductors have an intermediate size band gap, and the valence band is almost full and the conduction band is almost empty, but not quite. So some electrons do get up there and they do actually move and can be used to actually conduct electricity. Conductors always have energy, always have electrons available for conduction. In fact, sometimes the conduction and the valence band actually overlap, which means that the electrons will move into the conduction band really easily. But in general, conductors have electrons available because usually they have just one electron loosely bound to the structure and they're kind of ready to go. So that is really brief and really short because we're going to work on the participation problem, and that's probably going to take you a while. But the idea, the only thing you need to take away from this, there's no calculation involved or anything. This is the idea that you need to put in your mind and keep there. At 0K, all the electrons are in the valence band. I'm going to say this more than once. I'm going to say this again next time because you need to remember that. As the temperature rises, they gain energy, the electrons, and some of them move to the conduction band and become free. And when they do, they leave behind a hole. And that basically creates the charge structure of the entire system. So valence band, conduction band, and the gap between them is all you really need to remember for this time. Later on, we will talk more about how to deal with those two. You will never know the value of EC and EV. They are, they're stable for each type of semiconductor, but we really don't ever know what they are. We just talk about differences between them, like the band gap.